Hello, ladies and gentlemen, and welcome back to the end of the 2017 Cayley contest. We're on question number 25. A positive integer n, with n greater than or equal to 3, is called a Nilla number if there exists a positive integer x with x less than n, and there exists... Okay, this is a long definition. Okay, so... integer x, x less than n, and there exists a positive integer m, such that m is not divisible by x or x plus 1, and m is divisible by every other positive integer between 1 and n inclusive. Okay. So for example, n equals 7 is a Nilla number. How many Nilla numbers are there in this particular range? Alrighty. So why is 7 a Nilla number? So there has to exist a positive integer x, x less than 7, and there exists a positive integer m such that m is not divisible by x or x plus 1, and m is divisible by every other positive integer between 1 and n inclusive. Okay. So there's sort of two things going on. We need to find an m and an x for this one. I'm gonna, because I really don't understand what's going on here, we're gonna focus on showing that n is a Nilla number, and hopefully that will spark some imagination. So every number 1 to n inclusive. Alright, so I've got 1 to 7. The product of all these numbers is 7 factorial, but that's not the smallest number that is a multiple of all of these. The lowest common multiple of all of these would be, what's the greatest factor of 2 here? So it would be 2 to the 2, 3 to the 1, 5 to the 1, and 7 to the 1. And that's 420. So 420 is the smallest multiple of all of these, I believe. Okay. Now, does that actually matter? Well, I'm not entirely sure that it does, because it needs to be divisible by every other positive integer between 1 and n inclusive. And what possible value could I have for the other numbers for x? Because I need both x and x plus 1. So, alright. What could we have here? Suppose it were... it can't be 1, because how could any m not be divisible by 1? But maybe it's 2. So x would be 2, and then x plus 1 would be 3. And we'd have to have some m which is divisible by all the others. But then we'd need 6 divides m. But 2 divides 6, and 3 divides 6. So that definitely is out. So it's not going to be 2. So x isn't 2 in this case. What if it were 3 and 4? Well, again, 6 kind of messes things up. 3 divides 6, and 6 has to divide m, so 3 has to divide m. Whatever my m is. Okay, so that's out. How about 4 and 5? Well, the 6 is gone, so maybe I can't have numbers up to sort of a certain halfway point for my x value. Yeah, so what if I had something like 42? So 6 divides 42, 7 divides 42, 2 and 3 being factors of 6. I mean, really all we needed was 6 and 7 here. They divide 42. but 5 doesn't end in a 5 or a 0, and 4 doesn't. 40 and 44 are multiples of 4, but not 42. So this would make for a fine M, and 4 would make for a fine X. Out of curiosity, is 4 the only one that'll work? If I had 5 and 6, then both 2 would divide M and 3 would divide M, and that would force 6 to divide M, so no. And then 6 and 7, same sort of reasoning. Actually, the 2, the 3, and the 6 seem really kind of important there. They sort of narrow down everything. Okay. So we have an example. I understand sort of why this works, but more important than that, I understand that 6, 2, and 3, there's something going on here. So a question is it something that's important that will sort of stick with other or the Nilla numbers, or is it something that's just sort of popping up here that with 2, 3, and 6? And I think so. What was it? So if 6 divides M, all the factors of 6 must divide M. So that's not good. So X can't be a factor of some bigger number in the list. And so neither can X plus 1 as well. So everything I say for X can also work for X plus 1. And then why couldn't we have 6 being X or X plus 1? Because not just that it had a factor that was smaller, but we could get what's the relationship? Why did so I said at some point 2 divides M and 3 divides M, and then I said, well, that means 6 divides M. Why does this work? If A times B is equal to C, and this is the crucial fact, the GCD of A and B is equal to 1, then if A divides M and B divides M, that forces C to divide M. Okay, you see this working with the 2 and the 3, they make up the 6, but if I had something like 4 here, 4 has smaller factors. 2 times 2 is 4, but the GCD of these is not 1. And so you can have something that 2 divides, but and that doesn't mean that 4 has to divide it. Maybe if I bump it up to 8. So 8 is 2 times 4, but the GCD of 2 and 4 is not 1. And so I can have something that 2 divides and 4 divides, but that doesn't mean that 8 divides. For example, M equals 4. 2 divides 4, 4 divides 4, but 8 doesn't divide 4. Okay? It doesn't mean 8 definitely doesn't. It just means we can't conclude that. So it doesn't imply that 8 divides M. So we sort of have this GCD result. So let me see if I can sum up my thoughts here. If for some k greater than 1, kx is less than n, or kx plus 1 is less than n, then these won't work. And maybe it's best not to use the x. So if for some k greater than 1, m and n are already taken, let's say z. So kz is less than n, then, and actually, less than or equal, then z can't be x, and z can't be x plus 1. So that sort of narrows down what our x and x plus 1s could be. Right? When I look at 1, 2, 3, 4, 5, 6, 7, 2 has a factor that's bigger, 4 for example, so 2 is out. 3 has a factor that's bigger, 6, so 3 is out. Neither of those could be x or x plus 1. So really, and of course 1 doesn't work ever, so really we're starting looking at 4. And it happens that 4 does work. Now also, if for some a and b greater than 1, with ab equals z, and this is the crucial part, GCD of ab equal 1, then z can't be x, and z can't be x plus 1, because a and b would have to be less than z, like a lot less than z, less than even z minus 1, because a would divide m, b would divide m, and that would force z, which is ab, to divide m, and that can't be allowed. Okay? So, yeah. There we go. And so that throws 6 out of the mix, and then we're left with 4, 5, and 7. Those are the only possibilities here. And then it just so happens that 4 and 5 work. Okay. Now, what else is there? Now, if we look carefully at the definition of a Nilla number, both x and x plus 1 are in the range of 1 to n inclusive. That's why x has to be less than n here. I don't know whether or not that's useful. It's just something I'm noting, that x plus 1 doesn't lie beyond our range at all. Okay. So suppose I had a z that was either x or x plus 1. Then I can't factor it with an AB. With A and B both greater than 1, and A and B have a GCD of equal to 1. So that's impossible. Now, what, if anything, can we draw from that? So why does 4 work? Why does 5 work? Why does 7 doesn't work? But why can 4 be x and why can 5 be x? And I guess why can 7 be x? Although it can't. You'd need to have 8 here. Although if I did do it with 8, 7 and 8, and then I could do 60. Yeah. So if n is 8, x equals 7, x plus 1 equals 8, and m equals 60 would actually work just fine. So yeah, 7 and 8 work. So why are these pairs working? That's the challenge here. So if the GCD, so let GCD of A and B equal D. I don't know much about D, but it's not 1. So I can find a prime P that divides D. P has to divide A, P has to divide B, P has to divide Z. Now, so P has some factors of Z. So I can write Z is equal to P to the K plus some other stuff. But then if I write A is P to the K and B is that other stuff, they'll have a, like if I do prime factorization, so P to the K and then some other prime q to the L, and then some other prime r to the, I don't want to use m, so we'll say O. But if I do prime factorization, then I'd be able to split it into A is just all those primes P, and B is everything else, and that would have GCD of A and B equal to 1. So I know that any way I factor the A and the B, as long as they're bigger than 1, so either I can never factor A and B, so either A equals 1 and B equals Z for all factorizations, are the only factorizations. And the only way that happens is if Z is prime. Or, I guess, the B being the other stuff can't exist at all. Would have to be 1. And that tells me Z is A is a power of a prime. So x and x plus 1 must be powers of primes, which is something we sort of saw on the other page. Powers of primes. This is 2 to the 3. This is 7 to the 1. This is 5 to the 1. This is 2 to the 2. Powers of primes work. So they must both be powers of primes. And if we had something like 6 squared, then no, you'd have 4 and 9 are somewhere lower. And so since something divides 4, or since 4 divides m and 9 divides m, 36, which is 6 squared, would have to divide m. But, as I already said, if I had something like 27, which is 3 cubed, yeah, sure, 3 and 9 are smaller factors. But if 3 divides m and 9 divides m, at best we can say 9 divides m. You can't conclude 27 divides it. Okay. So they must be powers of primes. And we can also note they must be bigger than n over 2. Because otherwise then we'd be able to multiply by 2 and get to 2x, which is less than n. And so 2x being a multiple, so otherwise 2x is less than or equal to n, and therefore 2x divides m and x divides m. So that narrows down our searches in terms of powers of primes. What else can we do? So of these two, one must be odd, and one must be even. We got 2 consecutive numbers. Any 2 consecutive numbers, one of them's even, one of them's odd. But they're both powers of primes, and that means that one of them is going to have to be a power of 2. So that certainly narrows things down. Certainly narrows things down. One of x, or x plus 1, is 2 to some power. And then the other one, so if x is 2 to some power, then we need x plus 1 to be a power of a prime. And they could just be a prime itself. It could be a prime to the 1, but it's got to be a power of a prime. Or if x plus 1 is the 2 to the k, then one less than that, x must be a power of a prime. Okay, is this enough information to start attacking the problem? So our n values had to be between 50 and 2017, correct? So 50 and 2017, okay. So I think we should break this up based on powers of 2. So in this range, what have we got? Well, 32 is certainly a power of 2, 64, 128, 256, 512, 1024, and the next one would be 2048, and the reason I don't have 16 is because that'd be less than half of 50. We don't need 2048 because that's beyond 2017. So let's look at, either 32 is x or it's x plus 1. So let's look at the numbers above and below these. So 1023, 1025, 513. That one's out because it's a multiple of 3. 511, I think, is prime. 257, yeah, that's a Fermat prime. 255, that's out because it's a multiple of 5. 63, 127. 31 is a prime. 33 is not a power of a prime. Multiple of 5, that's not going to do it. 129 is a multiple of 3 and not a power of 3. Okay. So, let's get our red pen out. That's not good, no good, no good. So nothing involving 64. 129 is no good. I think 127 is fine. Not good. 1023, multiple of 3 there. Multiple of 5 there. Now I need to check whether or not, I'm pretty sure 127 is a prime, but I'm going to double check that. I think it's a Mersenne prime. 127 divided by 11, no. 127 divided by 7, no. Yes, it's a prime. Okay. Prime, prime. And they don't have to be primes, they just need to be powers of primes, but it's looking like everything is turning out to be a power of 2 and a prime number. 511, I don't remember if that is. So 511 divided by 19, no. Divided by 17, no. Divided by 13, no. Divided by 11, no. Divided by 7, oh, it is. It's 7 times 73. Okay. So that's out. So we won't have anything with 512. We won't have anything with 1024. So what could we have? We could have x plus 1 is 32 and x is 31. We could have x plus 1 is 128 and x is 127. Or we could have x plus 1 is 257, x is 256. So, when are those, for what ends are those going to work? So they have to be bigger than a half of n. So no, my x has to be less than, or x has to be greater than n over 2. Right, that's my other condition, because if it's too small, then we can divide with the 2x would be a factor of n, and therefore x would be a factor of n. So let's take a look at the case where x is 31 and x plus 1 is 32. So if x has got to be greater than n over 2, then that means 2x has to be greater than n. So what's 2x in this case? I think we're probably going to end up making a chart here. So 2x is 62. So my range of n's, it can be 50 all the way up to 61. The second n is 62 comes in. This all sort of fails. Because then 31 would be a factor of 62, which would be a factor of whatever little m we could find. Okay, 127 and 128. So n needs to be, so x plus 1 has to be at least n. So our range would start off with 128. 2x in this case would be 254. So n would have to be 253 or less. Okay. And then the last one, 256, and x plus 1 is 257. So we'd have 2x is 1024, so at most we could be 1023 with our n. And n would have to be at least 257 to get that x plus 1 in there. Okay, so now let's use our calculator and figure out a number of numbers in a particular range inclusive. So if you want to find a number range inclusive, you take the top number, subtract the bottom number, and add 1. Okay? So the number of numbers between 1 and 5 inclusive, so that's 1, 2, 3, 4, 5, the answer should be 5. 5 minus 1, that'd be 4. There's 4 numbers between 1 and 5, 2, 3, 4, 5, but we want to include number 1, so we add 1. Same thing here, 61 minus 50 is 11, plus 1 because we've sort of excluded 50 from our list. So 12 numbers. So we have 12 ones here. 253 minus 128 plus 1, 126. 1023. And I just realized 1023, that's not 2 times. 2 times that is 512. So n's got to be at most 511. Because if it were 512, 512 would have to divide m. 256 divides 512. Okay, 511 minus 257 plus 1, and we get 255. So that's the number in that range. Alright, so if we just add this all up, we get 255 plus 126 plus 12, and we get a total of 393. Okay, so that should be the total number of Nilla numbers. And if we take a look here, we do get to the very first answer. So we have A. And that'll be what we bubble in. Okay, so that certainly took a little while to figure out at least what we were shooting for with the x's and the x plus 1s. But, you know, powers of primes is not too bad. It's fairly clean. Didn't take us that long to actually work out these, you know, that 31, 32 was a case, 127, 128 was a case, and 256, 257 was a case. And then as long as we added up the ranges properly, and since we're so low, let's just double check. 61 minus 50 is 11, plus 1 is 12. 253, so it'll be, you'll need to end in a 5, so it'll be 125. So, yeah, plus 1 is 126. And I just did that one. If I added 1 to this, that'd be 512. Minus 256 would be 256, but I've added 1, so I subtract 1, and I added 1 again, so it should be 254 plus 1. Yeah, 255. Okay, So I buy it, and that finishes off the 2017 Cayley contest quite nicely. It's been a good contest, I would say. And the next multiple choice contest I'll be doing will be the Fermat from the same year, the 2017 Fermat paper. Of course, if you want something else aimed at grade 10, you can always look at Galois or even past Cayley's. But until the next video, have yourselves a wonderful day.